I am Professor Charlie Collins, and this is your daily dose of statistics. So today we will be continuing discussing inferential statistics, and this will actually be our last discussion of inferential statistics. And specifically, we will be going over hypothesis testing 4, which is the chi-squared test. So far we've gone over several lectures in the hypothesis testing piece. We've gone over introduction to hypothesis testing, one sample case, paired samples case, independent samples case, analysis of variance, and now today we will be going over chi-squared. And so like t-tests, chi-square actually has two types of chi-squared tests. One is a two-variable chi-square test, and the other is a one-variable chi-square test. The two-variable chi-square test is a test of independence. I'm testing to see if the two variables are independent from dependent or independent from one another. And the goodness of fit chi-squared is looking at just one variable and asking the question, are the frequency counts in each of these categories the same? And so we'll get into each of these more specifically. So let's talk about the use of the chi-squared test and how we can actually use chi-squared to be beneficial for us. And so chi-squared, so first let's talk about the chi-squared test of independence. So what we're looking at with the test of independence is asking the question, asking whether or not two nominal or ordinal variables are related to each other. Or in other words, are they dependent on each other? Is one dependent on the other? Or are they independent from each other, meaning they're not related? The chi-square goodness of fit test examines the equivalence of frequencies in one single nominal or ordinal variable, right? So it's looking at the frequencies of categories within a specific variable. So let's take a look at an example. Let's think about healthcare reforms, and we have a little video here.
This week's deadline extension may yet help some people sign up for health insurance, but it's not a cure-all for what ails the online system. Many Americans are falling through the cracks of the healthcare law, or find it all too confusing.
I thought that it was going to go through to the point where we were actually going to be able to get insurance.
As a fast food worker, Alan Thacker makes too little for government subsidies to pay the premiums he was quoted in the Federal Online Exchange. He can't afford them himself. Thacker should have been eligible for Medicaid, but Georgia declined to expand its program. No help there either.
I feel like I'm drowning, you know, and I don't know what I'm going to do.
It's a sentiment many Americans may share. In the latest AP-GFK poll, support for the healthcare reforms dropped to the lowest level since the law passed 4 years ago. 26%. 43% oppose it. But the majority of people, 54%, expect the law will move forward as is or with minor changes. Just 13% say it'll be completely repealed. New Yorker Jessica Wilt thought she was out of luck too, collecting unemployment when she first applied online.
Was a little surprised at my options being around $350, $400 a month. I just couldn't afford that.
She's now a freelance consultant, sometimes lobbying Congress for arts education. At tax time, her accountant said something didn't add up and told her to try it again.
One of the questions asking about income I had answered incorrectly, which changed the tax credit amount that was available to me. It just goes to show how confusing this whole process is.
Wilt got insurance just in time for the March 31st deadline, which has now been extended for those who've started but haven't completed an application and those with special circumstances. Cindy Sharp, Associated Press.
So let's say we are...
This week's deadline extension may yet help some...
Let's say we are interested in examining something like support for the Obama healthcare system, right, or the healthcare bill. So just for brevity's sake, we'll call it Obamacare. That's kind of what the news media has been calling it. So let's say we work for a polling agency and we take random polls of people's opinions. We take public opinion polls, right? And so we're interested in looking at support for the Affordable Health Care Act, or Obamacare. And so what we can do is, in one scenario, we can use something like chi-squared test of independence to ask a research question like, is there a relationship between those who support Obamacare and those who have actually registered for Obamacare? Right. So the idea being that if you've registered for it, maybe you'll be more supportive of it, right? Because you need it. So that could be a hypothesis that we're trying to look at here, right? And so in this case, we actually have two variables. We have frequency of support, so either you do support it or you don't support it. And then we have the frequency of registration, so people who are registered versus people who are not, right? And we can use that information. So let's say, we'll talk about the data down the road a little bit, but let's say we polled 100 different people, right? So what we would be looking at is the extent to which people who we'd be looking at the number of people for each of these, what would be 4 different categories, right? People who are registered and support it, people who are registered and do not support it, people who are not registered and support it, and people who are not registered and do not support it, right? And we would be comparing across those 4 different potential categories, or those 4 different categories, to see if there's a relationship between the 2 variables. And so we'll get down to the calculations of it later. So let's just keep this in mind, right? Say we're public opinion pollsters, and we're simply interested in wondering, in asking the question, is there a relationship between whether or not people sign up for it and their support for it? So say we're interested in that question. That's kind of our first question. Let's think about another question. Let's think that we want to get accurate representation in our polls across political affiliation. So we ask another question from the people that we're polling. We ask them, what is their political affiliation, right? Republican, Democrat, or Independent? And let's just say we clump all independents together regardless of what they are. And so this question would be relevant for a goodness of fit chi-squared test. And so we can ask the question of something like, did the poll sample equally, did our poll sample equally across political affiliation, right? So are we sampling evenly across the different political affiliations? And so in this case, right, we have one single variable, a political affiliation, Democrat, Republican, Independent, right? So this question is slightly different, right? So we're just asking the question, is there equal distribution across each of these categories for this one single variable? So now let's jump into what I want to do here is using this as our kind of running example. I want to get into calculating both test of independence chi-squared as well as goodness of fit chi-squared. So we'll go through each of these steps for both of them. So let's start first with calculating the chi-squared test of independence. So this test is a little bit different than what you've seen before on t-tests. Because we are not using interval ratio data at the outcome variable, we're using nominal or ordinal data, our sampling distribution doesn't have to be normal, right? Because it's this is a test that's considered what's called non-parametric, and what that means is it assumes that the distribution is not normal, right? And that's partly because we have categorical data. So our 2 assumptions here is that we have independent random sampling, so our sampling is random, right? And our level of measurement is either nominal or ordinal. So those are the only 2 assumptions that we need to make. And we really need to make the assumption that the level of measurement is nominal or ordinal, right? So our variables of interest have to be nominal or ordinal. Step 2, we need to state the null and research hypotheses. And so let's bring in our research question real quick for our test of independence. So we're asking the question, is there a relationship between those who support Obamacare and those who have registered for it? And so our null hypothesis here is simply, it's a statement. It's not numerical as some of the other ones have been. So it's making the statement that the 2 variables are independent or they're not related. right? So our null hypothesis is always the opposite of what we're trying to prove, or what evidence we're trying to gain. So in this case, the null hypothesis would state that there is no relationship, right, between the support for it and registration for it. Now, our research hypothesis is, of course, the opposite of that. This is the thing that we're trying to have evidence for. So our hypothesis is that the two variables are dependent, or they're related to one another. Right? So now let's move on to selecting the critical region. Now, just like with t-tests, we and the F distribution for ANOVA, we'll be using the chi-squared distribution and using degrees of freedom to identify our critical region. And so let's just look at some simulated data here. So this is just some data that I created, right? And so what you have here in the top row, you have people who are registered for Obamacare, right? So you have you have a total of 55 people who have registered for Obamacare, and you have 45 people who have not registered for Obamacare. In the first column, you have people who supported Obamacare, right? Support versus not support. And so in the second row here, support for Obamacare, you have a total of 40 people who support it, and then 60 people who do not support Obamacare. And so again, what we're trying to do is ask the question, are these two relationships, or are these two variables related to one another or dependent on one another? And so as you can see here, right, what it does is it breaks down the frequencies in each of these categories. So in the top left cell, for example, where you see the 22 there, what that's indicating is that there's 22 people who are both registered for Obamacare and support Obamacare, right? In the bottom right cell, the 27 there indicates that there are 27 people who are not registered for Obamacare and do not support Obamacare, right? And so that's what this breakdown is. It's showing the relationship both between registration and support. And just another quick note, you'll see our total N at the very bottom right cell, N equals 100, so we have a total sample size of 100. And you have the row marginals and column marginals. Now those are really important because those help us calculate our observed not our observed frequency, but our expected frequency, and we'll get into the calculation of that later. So just make a mental note that those are important, both the column marginals and row marginals. And basically, what those do is they add up the total number in either the row or the column, right? So, for example, you can see the 40 here in the second row under the row marginal. And what that's doing is it's adding 22 plus 18, right? And so that's basically what we're looking at. So let's get into selecting our critical region now that we have an understanding of our data. And so again, we use the chi-squared sampling distribution. We select our alpha level of 0.05, right? This gives us our 95% confidence. Now, degrees of freedom here are a little bit different, right, than what you've seen before. And so here it stands for rows, the R, and then the C is number of columns, right? So we have 2 rows and we have 2 columns. And so when we do the calculation there, we have 1 degree of freedom. So in this calculation, what we're doing is doing number of rows minus 1 times the number of columns minus 1. And we end up with degrees of freedom of 1. So now let's take a look at our critical values for the chi-squared distribution. And so this table I pulled off of the internet, so it may look a little bit different from your book, but not completely different. So what we want to do is first find our alpha level. So we're using the 0.05 level. And then we want to find our degrees of freedom, and we're using 1 degree of freedom. And so what we do is we follow the row all the way down from 0.05 and then follow degrees of freedom over, and we have our critical region of 3.84. Right, so what we're trying to do here is we're testing when we calculate our observed chi-squared test. We're asking the question, is our observed chi-squared beyond this critical region of 3.84? So now we have our chi-squared critical region of 3.84, and what we'll do is we'll bring that with us down the line and use that to compare to our chi-squared observed. So now let's move on to computing our test statistic. So this is interesting because you have to both compute the expected frequencies as well as your observed frequencies. And expected frequencies means basically what should the number in each cell be, or what should the frequency in each cell be, if these two variables were not related, right? Just by given random chance. And so that's what our our expected frequencies do. And so our expected frequencies, and so this is why the row means, or the row marginals and column marginals are important, right? Because we use those to calculate. And so if we take a look at the expected frequencies, say for the top left column, or excuse me, the top left cell here, where we have the 30 registered for Obamacare, what we find is that we can create our expected frequencies for registered supporters, so people who are registered and support Obamacare. So what we do is we take our row marginal, which is 40 for that one, and we take our column marginal, which happens to be 55, we times those together, and we divide by n. And so what we need to do is, and then we come up with 22. So what I like to do, just to kind of simplify this for myself, is I'll actually put the number in the cell kind of in parentheses or in a different color or something like that, just to help me remember, right? And so we need to do that calculation for all 4 cells. So I'm not going to do that. I'll leave that up to you, so I'll just plug in the numbers here. So I'd recommend maybe just pausing the video, taking some time and calculating a couple of these, or maybe all 3 of the rest of them, just to make sure that you can do it. Right, so that one's going to be 18, 27, and 33. And so now what we do is we need to calculate our chi-squared of the obtained value. Now what this calculation is saying is that we are summing in this case we'll be summing 4 different equations, right? So we'll be adding the 4 equations together, and you'll see what I mean. So this f sub 0 is the frequency of the observed. So again, in the top left cell here, it would be 30, minus the frequency of the expected. So again, top left cell would be 22. All divided, and then we square that, and then that's divided by the frequency of the expected. So we'll just go through each of these steps here. So I'll start plugging in numbers. So let's start with this first one here. So we have our base of equation, right? So what we do is we plug in the 30 into the frequency of the observed. Then we plug in our 22 into the frequency of the expected value. And then again, the frequency of the expected value. And then we can do that for each of the cells, right? So we'll just plug those numbers in. Each of the cells plug those numbers in, right? And the last one plug those numbers in. So once you go through the math of this, squaring, minusing the observed from the expected, squaring it, and then dividing it by the expected, what we come up with, and then adding all those together, or summing them together, what we come up with is a chi-squared of the obtained value of 10.78. So again, what I would do is I would recommend just pausing this real quick, going back and calculating this by hand, just to make sure that you can get it. So now that we have our chi-squared of the obtained, what are we asking? What kind of question are we asking? Well, what this shows us is that our obtained value is beyond the critical region of our chi-squared from our chi-squared table, right? Of our expected, or not our expected value, but of our critical value, right? So 10.87 is larger than our critical region of 3.84. And so what we can do with that is we can now reject the null hypothesis, right? And so now let's think about making a decision and interpreting the results. And so let's look at our question here. Is there a relationship between those who support Obamacare and those who have registered for it? And what we find is that we see our null hypothesis here and our research hypothesis. And what we find is that we have support for our hypothesis, for our research hypothesis, and we do not have support for our null hypothesis, right? So we're 95% confident that the two variables are related to one another, or they're dependent on one another. And so you might want to write up something similar to this. A chi-squared test of independence revealed a relationship between people who registered for Obamacare and those who support it, right? And so we have in our data here, in our little data summary, we have our chi-squared with our degrees of freedom of 1, which is in parentheses, equals 10.78, so that's our observed chi-squared value, with a p of less than 0.05, right? So that's our alpha level. Remember, our what we always fall down to for our alpha level typically is a probability of less than 0.05. And so that creates our data, and that shows us how to interpret this. So that's walking through the models of calculating chi-squared test of independence. Now let's take a look real quick at the 5-step model for calculating chi-squared goodness of fit. And you'll see a lot of similarities here. There's just a few slight differences. So making the assumptions are the same, right? Independent random sampling, level measurement is nominal. The difference here is we're working with one variable instead of two. State the null and research hypothesis. So again, let's take a look at our goodness of fit research question. Did the poll sample equally across political affiliation? Right? And so we'll have our data here in a second. And our null hypothesis is that there is no difference in number of people by political affiliation or number of people in the sample. And our research hypothesis is that there is a difference in the number of people by political affiliation. So one political affiliation was sampled maybe more than another political affiliation. Now we need to select the critical region. And so let's take a look at our sample data. So again, we have a sample size of 100 here. 35 plus 45 plus 20 is 100. And so we have our question, which is Obamacare support, and this is our poll sample. So we have 35 Democrats, 45 Republicans, and 20 independents. And so again, we're asking ourselves the question, is there significant differences in the frequencies of Republicans versus Democrats versus independents, right? Was one group maybe sampled significantly more so than the other groups? So again, same sampling distribution, same alpha level. The degrees of freedom here is slightly different. So again, in this case, remember back when we were talking about ANOVA, K always means number of groups, right, or number of response options. And so in this case, we have 3 response options: Democrat, Republican, Independent. That's 3. We take that and minus that by 1, and we end up with the degrees of freedom of 2. And so again, take a look at our critical values. So we go to our alpha level, go to our degrees of freedom, and we have our critical value of 5.99. And so we have our chi-squared critical, 5.99. We can use that to compare to our observed chi-squared value, which we will calculate here. And so the test, computing the test statistic in goodness of fit chi-squared is not quite as complex because we don't have that first step, right? We have, well, we do have calculating expected frequencies, but calculating them is a little bit easier. And so for expected frequencies, what we're doing is we're assuming that all categories are the same, right? So we expect that on any given chance, we should have equal categories, right? So we should have a third Democrats, a third Republicans, and a third Independents. So what we do here is we take the sample size and divide that by the number of groups. And so our expected frequencies here for each case is going to be 33, right? 33.33. And so we use, and then now when we're calculating our chi-squared of the obtained value, what we're doing is we're assuming that expected frequencies are all the same, right? So we use the exact same calculation as we did with the right? So we can start plugging in our numbers. We have our 35 here, we have our 33 here and here, and then we can just start building out the equation, right? And so what you see, right, so this equation here is very similar. It's the exact equation from test of independence. Right? And so once we calculate all this out, what we find is we have a chi-squared obtained value of 9.5. And so again, we can compare that to our chi-squared critical region of 5.9 or 5.99. And we can, in this case, reject the null hypothesis because 9.5 of our obtained value is greater than the 5.99 of our critical value or our critical region. So let's make a decision, right? So we have our research question here. Null hypothesis, there is no difference in the number of people by political affiliation. There is a difference in the number of people by political affiliation. And so again, we reject the null hypothesis. So what we're stating is that there wasn't equal sampling across 3 political affiliations. And so what we can state is something to the effect of the goodness of fit chi-squared revealed that the sample for the Obamacare poll did not sample equally across political affiliation. Right? So there weren't equal categories. And so again, we have our chi-squared with our degrees of freedom in parentheses, 2 degrees of freedom. Chi-squared obtained value is 9.5 with a p of less than 0.05. So we've taken a look at now both our 5-step process for calculating chi-squared goodness of fit, as well as calculating the test of independence. So that concludes our lesson on hypothesis testing. So next time we will be moving forward into inferential statistics, or excuse me, into bivariate statistics, and talking about the relationships between 2 variables. And so that concludes our section on inferential statistics. And this has been your daily dose of statistics.